Good morning and good afternoon, everyone. Looks like we've got quite a few folks jumping in here. We'll get things started in just a moment. All right, we are super excited to have you here today with us for our webinar, Lifting the Veil, the Importance of Data Transparency for Remediation. Thanks for taking the time to join us today. I am Sue Bruning, Vice President of Marketing and Communications here at Cascade. I am the voice behind the camera and your moderator for today's broadcast. While we wait for everyone to log in and join us, I want to congratulate Jim Price with Spencer Fain, LLP, who is the winner of this webinar's drawing for a free lunch. And if you're not familiar with what I'm talking about, before every webinar, we draw a name from our registrants who submitted a question while RSVPing for the webinar, and they'll receive a gift card to enjoy something tasty. So the next time you register for one of our webinars, take a few moments to submit a question to our presenters, and you'll be eligible for the drawing. So Jim, please check your inbox for an e-gift card from Uber Eats. Our presenters, Elliot Cooper and John LaChance, will begin the presentation in just a moment. And before I turn the floor over to them, I wanted to cover a few logistics with you. All of our attendees are in listen-only mode, but at any time during the presentation, you can type a question into the question panel that's found on the right side of your screen. And at the end of the presentation, we'll address those questions as well as the ones that were submitted with the registration. During the Q&A time, you can also click on the hand icon, which allows me to unmute your line. And finally, this broadcast is being recorded and will be posted on Cascade's website on our webinar page for you to check out on demand. All right, that covers it for the logistics. If you're just joining us, welcome to the webinar, Lifting the Veil, the Importance of Data Transparency for Remediation. Super glad that you're here with us today. If this is the first time you're attending a Cascade webinar, I'd like to extend a special welcome to you. Cascade Environmental is a field services provider that offers drilling, site characterization, and remediation. Everything you need from project concept to completion. Together with Hrse, we offer consultants access to the nation's largest fleet of equipment, the deepest bench of technologies to choose from, and industry-leading experts like Elliot and John here today, who can help you get the results you need. You can learn from and connect with many of our experts in our regular monthly webinars. So now I'd like to introduce you to Elliot Cooper, Vice President of Technology with Cascade Environmental, and John LaChance, Vice President of Development with Hrse. Elliot and John are frequent presenters on our webinar series, and they love to share their extensive expertise. Both have careers in the environmental remediation industry spanning 3 decades. Elliot helps clients design efficient and cost-effective remedies using high-resolution site characterization and a vast array of remediation technology options. His specialty is finding the right combination of tools and technologies for complex sites and ensuring every step of the remediation process is optimized to achieve your results. John is an internationally recognized expert in thermal remediation, having worked on projects in the US, Brazil, China, Australia, and several European countries. Today, John helps clients select thermal technologies that will meet regulatory requirements, eliminate liability, and enable the resale or reuse of their property. John, Elliot, we're all looking forward to hearing your insights today on data transparency. So without further ado, I'll let you take it away.
Great. Thank you, Sue, and glad to be joined by John here. So we've got a packed full agenda today. We're going to talk about the injection side of the business first, and then we'll switch over to in situ thermal remediation, and then we'll finish up with a Q&A session. We'll go through this agenda in more detail, but this will give you a quick idea of what we're going to be addressing. So what is lifting the veil? I've looked at a lot of definitions, and this one seemed the most appropriate. To divulge, explain, or reveal something that was previously a secret. So that will raise a question right from the start of what could be a secret in our industry, but I think we'll get to that as we go through the different slides. So first of all, I'd like to talk about what you need to know, which is really falls in line with lifting the veil. In terms of chemistry selection and dosing. And so the things I look at are if treatability testing, excuse me. Sorry about that. If treatability testing is done, is it representative and can it be scaled up? Do we understand contaminant mass in soil, groundwater, and DNAPL phases? Are there any scavenging reactions that we have to account for? What's a good basis for the number of injection events for a project? And then something close to my area of expertise, can the physical form of the chemistry be adequately distributed in the proposed lithology? So in terms of contaminant mass, the point here is in terms of transparency, there's really three scenarios. You've got a turnkey project where you've asked the vendor to provide you with a design, the chemistry, and the delivery, or you've developed the design and selected the chemistry, and you've reached out to a vendor for delivery. And those are really the two scenarios. And so in the case where you're getting the design and the dosing, it's really important for you to understand all the contaminant mass distribution in the various phases. And then also what kind of porosity is going to be used. Is it effective porosity? Is it mobile porosity? It's really important to understand that as part of the design that you would receive. We need to also understand how the absorb phase is going to be treated and managed over the life of the project. So when you get a design, I think it's critical to get that information. The other thing is, how do we develop the number of injection events? And so there's a lot of different approaches to that. I think it's very important to understand, is all the absorbed and dissolved phase being treated in one event, or is there some accounting for matrix back diffusion that will allow or provide you with the information to be able to come up with a rational basis for the number of events? And in this slide, basically what we're doing here is coming up with a basis for the amount of oxidant we'll need based on the mass in groundwater and soil, but we're also taking a stab at what kind of back diffusion rates we're going to get and how much oxidant we can inject in each event without wasting any of the oxidant. So very important to understand how the number of events is developed, the basis, and not just rely on a rule of thumb. And then here you can see what we've done here is we've taken the total amount of, in this case for sulfate, that we're going to inject. We divide the total amount that we need stoichiometrically, and that tells us we're going to need 3 events. So if you're getting a design from somebody, it's very important that you understand how they're reconciling what's sorbed in the soil mass, in the dissolved phase, and if there's DNAPL, that's even more important. So these are very items that require high transparency for you to assess the type of performance you're going to get on your project. So then we move over to the injection design, and there's key issues here that need to be understood. You need to know what's the design basis for the radius of influence, what's the design basis for the injection volumes to be injected, which relates directly to the radius of influence. What's the basis for the target interval you're going to inject into, and then your basis for the delivery approach. And then also, we'll talk about pressure and flow limitations that are very important when you're looking at making contact. And then also a subtlety, but what's the basis for where these injection locations are placed versus where the monitoring wells are located. So in terms of radius of influence, we've talked about this for 15 years in different webinars. And on the right, you can see that's probably your ideal case of a core 10 feet away from an injection zone with potassium permanganate. So you can see, you know, that's the golden goose we're trying to achieve, and obviously that's more difficult as we get into heterogeneous sites. But it really comes down to understanding the mobile or effective porosity, the volume you're going to inject, how much additional flow you're going to get by advection, and then that'll add up to your radius of influence. And so in this case, you know, 11.5 foot radius of influence is achieved by injecting 20% of the pore volume, effective or mobile, depending on how you look at it. Additional 8 feet of effective distribution, and that all occurs in 16 days. So the other thing you have to take into account is the residence time and persistence of your chemistry. So that 16 days becomes important when, let's say, you've got very low seepage velocity or flat gradient, and it's going to take, you know, 180 days to reach 11.5 feet. So that's radius of influence, and that's key in terms of a transparent information on a project. The other one is in a design, what's going to be targeted? Is it going to be the transmissive zones, the storage zones? We all know that in most sites, 90% of the groundwater flows through 30% of the cross-sectional area. Am I going to, is the design based on injecting into that? Or is the design going to focus on 10% of the groundwater that flows through 70% of the cross-sectional area, which is typically, you know, fine-grained material? Am I going to go after that by fracturing or enhancing permeability? And you can see on the left, there's somebody struggling with that decision, and believe me, that's a critical decision in a design and approach that you've got to understand moving forward. So just in terms of direct push approaches, it's really critical to understand, are you going to be injecting at a discrete interval, as I show here on the left, or are you going to be injecting through a temporary screen, as I show on the right? So as you review designs and approaches, it's really critical to understand the tooling that's going to be used, as well as whether that's going to be implemented in a top-down or bottom-up approach. And so we get into this situation where maybe the design is going to be just targeting transmissive zones with direct pusher wells. And you can see here that we can do that with injections, direct push screens or well screens, and we can intercept the high perm zones and get amendments into those transmissive zones. And that's an example of a injection tool that can be used to accomplish that kind of distribution. When we look at the both low and high K zones, a lot of projects want to target everything. It's really important to understand that that's what you're getting. And in that case, you're going to have to use a more aggressive targeting approach with a jetting type tool to really make sure you can get amendment in both the storage and transmissive zones. So two key pieces of information that should not be transparent, and that is what's being targeted and how is it being targeted. That's very important. The other thing we look at is the direct push rigs and tooling, the pump selection, the mixing equipment, the flow and pressure measurement. And I always come down to, at the end of the day, it's all about the pump and how we can control it and manage it. And so it's very critical to understand what pump you're getting on a project. So when we look at direct push drilling, for example, these are key items. I won't go through all of them, but these are the type of information that you need to obtain as you move forward on a project and selecting an approach and a contractor, or how you're going to do it yourself. And so you can see here with direct push drilling, there's the drill rigs, the type of tooling, whether or not you use inner hose, how do you overcome refusal, how are utilities marked and hand cleared. And all these have direct and indirect impacts on performance optimization. And in this case, they can have direct in that the type of tool can definitely impact the type of distribution you would achieve. But they can also have indirect in that, what I like to say, it takes your eyeball off the task at hand. And there's a lot of things to focus on. And if you're focused on things that aren't going right, then you've got less time to focus on the things that you've got to get right, which is the actual delivery and contact of the amendments. And there's just another tool. The pumping systems, obviously, like I said, that's critical. It has a direct impact on the performance. You really need to know the pump type, its pressure and flow curves. Does it have to be calibrated? Can it handle liquids versus solids? Is it compatible with corrosive? How is it powered? Does it need pressure relief? Does it have a variable speed drive, or do you need to recirculate? And how is that pump going to be manifolded? So you can see here, this is a direct impact on your results. The manifolding is also important because that's going to impact your cost. And so the ability to optimize through manifolding is something you need to understand. How many points? How's it going to be done? How the points are going to be started up? All that type of information is going to be very critical for you to be able to understand the performance and measure that in the field. Amendment handling and reconciliation. This is always a good one because you don't want to end up at the end of a project with too much amendment or too little. And so that has an indirect impact typically, unless you don't have enough left over, and then that can obviously have a direct impact. So things you need to understand is how the liquids are going to be transferred, how the bulk solids are going to be transferred, what's the packaging versus the performance in terms of how efficiently you can mix, what's your inventory going to look like, how are you going to store it, are all these amendments compatible with each other, and then how are you going to decon everything when you're done. These are all important factors that you need to understand. And then mixing. Mixing is critical because if you don't get a uniform mix, then you're not going to get to a point where you're going to get good distribution. And so there's issues like inline mixing, batch mixing, the tank size, how you're going to mix liquid and solids. Are you going to inline inject something like dihalococoides? How to handle overflow? Are you going to pulse mix, or do you need to filter? What kind of ventilation and air monitoring requirements are you going to have with bulk solids? And then here's just some shots of different liquid amendment mixing capabilities, but generally they're totes, they're tanks, small tanks, large tanks, and sometimes intermodal containers. You really have to have a very good understanding of how mixing is going to occur on your project. When we look at pre-mob, really the key issues here are going to be what's the footprint of the site, the equipment, how's everything going to be delivered, is there secondary containment, exclusion zones and decon, water and leak tests, rental equipment being delivered, scheduling, night or day work, work hours, DOT restrictions. All important things that need high transparency. And then safety. I don't mean for this to be last because it's first, but it's often overlooked. But there's key items for safety, and that is the health and safety plan, the site data sheets, the JHA, JSAs, standard operating procedures, PPE, what PPE is going to be used. Our experience, it's all over the map, and you want to make sure you or your contractors are protecting themselves. A spill control plan, PFDs of the operation or the equipment to understand how it works and what safety issues could be. Tailgate meetings and near miss reporting, training of the folks, and how do you manage short service employees. So safety is another, it's an indirect issue, but if any of these things rear their ugly head, then they can have a direct issue because, like I said, they take your eyeball off the project. What else do you need to know on injection? Really, we look at, you need to understand if shakedown and distribution testing is going to be performed. How is everything going to be monitored, and what are approaches for troubleshooting? So we all like to do distribution testing when we can. We also call it design optimization testing. And on the right is a picture of a project where verified distribution through hydraulic fracturing of an amendment with a green dye. But we really need to understand, are you going to take cores? Are you going to do electrical conductivity logging? Are you going to monitor the wells for parameters? Are you going to use test kits? What actual pressures are you going to see during the test? Is depth and refusal a problem, which it can be? The tooling, what works best, top down or bottom up? What tooling works best in terms of tool diameter and the hose diameter? So critical information that directly impacts the success of your project. And then on the injection logs, really what you've really got to understand, and this is critical, especially when you're going back to understand post-injection monitoring results. How's pressure flow going to be measured? How are you going to measure the time amendments are injected? How do you reconcile inventory, make sure you're on track? Whether or not you need to measure air quality for certain projects. Are you going to use digital or manual recording devices? Do you truly understand the depth that you're at, what intervals you're at, and the boring locations? And so these all have direct impacts on project success. And on the right is just an example of a digital system, automated system that we have that really sort of take the error and uncertainty out of performance monitoring. But typically, this is what you're going to at least want on a traditional injection system. You're going to want a weekly summary. You're going to want the amount of amendments injected, total solution, batches mixed, and then you want to accumulate that data over time so that you have a running total. So this is the minimum information you want on a project at the high level. You then want to get into the actual injection locations where you want to understand each individual well or direct push location. And then you want to be able to go in and measure pressures and flows and the amount of amendments and total solutions at each individual point and at each individual interval. So this is what I would consider the bare minimum to have to be able to understand what happened during your injection event. It should be totally transparent. If we go with a digital approach, you're going to eliminate all this uncertainty, where in this case, we're able to track pressure and flow continuously, and you can have no uncertainty as the averaging time, or was it recorded effectively manually, and things like that. So while it's not a requirement in terms of transparency, we believe it's the next step in terms of transparency related to how the injection event went. And then troubleshooting. I'll finish this real quick. Not everything goes right on injection project. You know, it's hopefully it's man versus geology and not man versus equipment. But things that you need to understand how troubleshooting can occur. And those are things like pressures and flows are not what was expected. You've got refusal, you're getting daylighting, you have to skip intervals, you've got weather conditions that are adverse, equipment's breaking down, which hopefully, you know, that's kept to a minimum. The actual versus recorded volumes aren't lining up. What are you going to do with the daylighted material? What do you do if you have to step out for utility? And what do you do when you have a lot of back pressure that's slowing down how you remove your rods from the target interval? So troubleshooting is, you know, it can be done on the fly, but I think it's also good upfront to understand what are the troubleshooting sweet spots that might be encountered. So at that point, I think I gave you a lot of information on what you need to know, whether you're designing a project yourself and subcontracting out the injection, or whether or not you're getting the whole enchilada from a vendor. Those are the key things we believe need to be 100% transparent, and will just help ensure that you get what you wanted or expected. Now I'm going to turn it over to John on in situ thermal remediation, and he's going to go through the same type of process. Thanks, John.
All right. Thank you, Elliot, and great job on lifting the veil on how we design and implement effective injection technologies. That was awesome. So as Elliot said, we're going to turn our attention now to how this sort of a similar approach to lifting the veil or providing some transparency in terms of how we design, well, select technologies, design and operate thermal remediation sites. So to kick it off, you know, we have this basically just a summary of what in situ thermal remediation is. It's a bit different than injection, although it requires a lot of boring and a lot of points in the subsurface, but we do something a little bit different in that we add heat. Our main objective is heating up the subsurface. So we have a treatment area footprint. We put wells or electrodes or steam injection points as a way of adding energy to the subsurface to increasing the temperature. And we may have a variety of target treatment temperatures that we're aiming for, but typically for CVOC sites, most VOC sites, and most of our projects, we're heating the subsurface up to 100 degrees C. That generates COC vapors, but it also generates steam vapors, and the COCs partition into the steam, and then we have an extraction system that pulls all of that out of the subsurface and sends it to a treatment system. So, and big picture, that's basically what in situ thermal remediation is. The technologies that we have in our capability to implement or to use at these sites to heat up the subsurface is thermal conduction heating, and that basically is where we drill holes, put pipe in, and we put a heating element in, and we heat the subsurface via thermal conduction. We also have electric resistance heating, which is where we put electrodes in the subsurface, and then we apply a voltage potential to those electrodes and encourage or promote current flow between the electrodes, and it's the resistivity of the soil to that current flow that generates heat or heats up the subsurface. We also use steam injection, and that's where we basically have a small injection screen, typically 1 to 2 feet long, and we target specific intervals to inject steam, and then to develop steam zones within the subsurface that envelop, surround and envelop the target treatment zone. And in some cases, depending on the geology, we use both. We can use a combination of TCH and steam or ERH and steam to heat up the subsurface. And all of these technologies, we are applying at least vapor extraction to remove that steam and those COC vapors. But in some of these applications, like where we're using steam, we'll also extract groundwater to provide not only pneumatic control, but also hydraulic control. So we don't want to spread contaminants, we want to remove everything in the subsurface. In situ thermal remediation is really primarily a mobilization technology. What we want to do is mobilize the contaminants out of the hard to reach or hard to access zones, the DNAPL, the low permeability zones, get that into the Vados zone where we can extract it and send it to the treatment system. So how do we choose? Well, first off, we start with COCs. We look at what are our contaminants that we're targeting. And primarily we're looking at volatilization and steam stripping to get those out of the subsurface. But if we look at the low temperature approach over here in this green section of the figure here, this is actually not targeting volatilization as much as it's targeting the degradation. So either bio or abiotic degradation mechanisms. So when we heat up to 35 C or so, we can promote biological degradation. And if we take temperatures up to 70, 80 degrees C, we can actually promote abiotic degradation mechanisms such as hydrolysis. And so for certain COCs, we can do a very good job with that. The nice thing about that is we don't need vapor extraction and treatment systems, so it can be very cost effective. But again, for the bulk of our sites, we're looking at treating to 100 degrees C or heating the subsurface to 100 C, and we're targeting VOCs, BTECs, CVOCs, as well as some of the lighter end semi-volatile compounds like naphthalenes and chlorobenzenes. And then we always have the ability to go to higher temperatures depending on if we're targeting PAHs, PCBs, even PFAS, we can heat sites to higher temperatures. But primarily, again, most of our work, most of what we see from site remediation for in situ thermal is targeting 100 degrees C. And for that range, we actually have a bunch of options, right? It's the TCH, ERH, steam, and different combinations. So how do we choose? Well, once we kind of know what our COCs are and we're looking at 100 degrees C treatment approach, then we start to look at what geology are we targeting. So what is the specifics of the site? And a lot of our sites have a mix of geology. So we might have sand and gravel units, we might have silt and clays, we might actually get into saprolite or fractured rock. So we need to kind of look at all of these and evaluate how these technologies or combinations would do. The key parameters based on these technologies are the thermal conductivity of the soil or the rock, the electrical resistance. Again, this is when we're looking at using ERH, and the permeability. Permeability comes into play not just in terms of being able to inject steam in the subsurface and for effective heating, but also in terms of assessing how much groundwater flux below the water table we might have in a zone. So we have to evaluate all of these. What we find though is that thermal conduction heating is a great fit, and that primarily for a lot of sites, and that's because of the uniformity of thermal conductivity. When we look at thermal conductivity for all the different types of materials we have in the subsurface, the minerals, sedimentary rocks, volcanic rocks, et cetera, we have a range, total possible range between 1.5 to 7 watts per meter Kelvin. So that's a pretty tight range when you consider permeability or resistivity, which we'll talk about in a second. And so what we see is the site variation is generally within a factor of 2 to 3. That's pretty narrow. So electrical resistance heating, when we look at that, that's based on, again, the electrical properties, so the conductivities or the electrical resistance of the soil. And what we find is that the optimal range is 10 to 500 ohm meters, and that's a measurement of the resistivity of the soil. Why is that? Well, we can do sites that have lower resistivity, meaning they're more conductive, or we can do sites that have higher resistivity, but that requires special equipment, it requires higher voltages, it requires a lot more current, and it just makes it more complicated to do it. And in some cases, maybe more risky. If we have to use high voltages at those electrodes, we can run into stray currents and voltages that might be an issue for workers or for building infrastructure. So we tend to see this range of 10 to 500 ohm meters as being pretty ideal. So when we look at the range of materials, as this figure shows here on the right, what we find is that for ERH, we're going to, silt and clays are always going to be a good fit. Some sedimentary rocks like shales and sandstones and weathered rocks, may be a good fit. Igneous metamorphic, dolomite, limestones, those are going to have much higher resistivities, and those are not going to be great fits for ERH. Solid bedrock itself is not conductive to sufficient levels for ERH heating, so it is just too resistive. We just don't use it. So again, you know, for the sites where we have optimal resistivity, we can use ERH. Where we have sites with much higher resistivity or much lower resistivity, we can then use thermal conduction heating. So we look at choosing the right technology for the site, not trying to use one technology for all sites. And again, where we have high permeability and potentially high groundwater flux, we can then use steam alone if that's the entire treatment interval, or we can combine steam with the other technologies to address the groundwater flux and to do a good job of heating. And generally what we find here is that steam is a good fit if we have basically 1 Darcy or greater in terms of permeability, or if we think about it in terms of centimeters per second, it's like 10 to the minus 3 centimeters per second. So if it's higher permeability than 10 to the minus 3 centimeters per second, that's good for steam. If it's lower, it's not so great. And again, what we find here with steam is that, you know, it's very dependent on the permeability. Unlike thermal conduction, permeability ranges by many orders of magnitude at a site. So again, this is why thermal conduction heating or TCH combined with steam, or even ERH at the right resistivity ranges combined with steam, make good applications for a site. And again, this issue of groundwater flux, it's important, and I think Elliot touched on this before, but 90% of the flux occurs in less than 10% of the cross-sectional area, and that's because of the effective porosity or permeability of these formations. So when we look at data from a site, it's important to have good hydraulic conductivity data and discrete data, so over particular units, so we can understand where we might have and identify where we might have high flux zones, so that we can design systems around that high flux zone to address it, and if we need to add steam to do a good job there. So let's talk a little bit more about design and lifting the veil on how we do the design. I kind of think of this as, you know, getting a quote to paint your house. You may get 10 quotes or 5 quotes. They range in price, but until you dig into it and see what kind of paint are they using? Is it oil-based? Is it water-based? How many coats are they applying? Are they brushing your house or scraping your house first? What are they doing for cleanup? How many people are going to be out there? You really can't compare those numbers, because you need to understand what goes into that design in terms of then understanding what you're actually getting for that price. What is the quality of your house paint going to be? How long is it going to last? How's it going to look? How much mess is going to be in your yard? You have to do that. You have to look at the details. So that's what we're going to look at here relative to thermal. The important thing with thermal is you got to get it right. These are not simple systems. They're complicated. They can involve quite a bit of infrastructure, again, quite a bit of drilling. So you better do your homework up front and do, select your technologies, but also do a good job in designing, because it's pretty hard to overcome mistakes you've made up front once you get into implementation. So let's start with something very basic to thermal, which is we got to add energy to the subsurface. So what this graph shows you here is an example site, 5,000 square meters, which is roughly 53,000 square feet, so a little more than an acre. And we're using ERH here. So we have 2,000 watts per meter input into the subsurface. What that means is for each meter length of electrode, we're putting 2,000 watts in. And that gives us a heat up here of, this gives us energy density input, and then this gives us for different spacing, we get the number of electrodes, and we can actually look at, and this could be heaters too, we'll talk about that in a second, but if we have, for example, 6 meter spacing between our electrodes, we'd have a little more than 250 electrodes over this area. And we'd have ultimately roughly around 90, a little more than 90 watts per meter cubed going in. So this is important. Again, how many coats of paint, how much energy are you putting into the subsurface? What is your design assumptions? What is the unit length power input, whether it's ERH or TCH or steam? How much steam are you injecting into the subsurface? And then looking at the spacing that you have for these things. It's important to consider this issue of heating outside versus not heating outside. And a lot of times, if this is your treatment zone, we'll see designs where folks come in and just have ERH electrodes or TCH on the inside. That's not sufficient because you want to heat the entire perimeter. You want to treat everything out to here. So you need to have some heaters on the outside or ERH on the outside to ensure that happens. Also, importantly, if you don't do this, then you have a situation where you're heating on the inside, creating steam, and it's pushing to the outside. An outside perimeter of heaters or electrodes pushes and provides that hydraulic and pneumatic control. So when we look at this for ERH, for example, pretty standard spacing is somewhere between, this is in meters, but it's roughly 18 to 21 feet. If we look at that kind of spacing, 2,000 watts per meter, that gives us 54 to 85 watts per cubic yard. So that's a pretty good, that's what you want to be looking for in terms of the proper energy density to achieve cleanup within 6 to 8 months. If we decrease that spacing, we can get much more into the ground, and we can actually treat a little bit higher groundwater flux rates and within that same time period. And then if we if we're using thermal conduction heating, we'll use much smaller spacing. It's obviously a lot more heaters, but this is where we can achieve temperatures of greater than 100 C, as much as 350 or 400 C if necessary to treat PFAS, PCBs, and such. So let's take a look at how we do this, how we use these numbers. And again, this is getting into the detail of the design. So it's not enough just to say I'm giving you 100 heaters, 100 electrodes, and it's going to be done in 6 months. You want to ask some specific questions. One is, what is your spacing? Are you including perimeter heaters, electrodes? This is key, as we just saw. And what is your average power density going into the subsurface? We want to target somewhere in the range of 70 to 80 watts per meter cube to get effective heating at these sites. And once we do this, this is where we get our total power load, or what we need from the utility to heat the site. You also want to know what's going into those calculations relative to assumptions about porosity, about saturation. This is all going to calculate or come into play in terms of how much energy. So we have so many heaters or electrodes or steam injection wells, we can put so much energy in over a period of time. We have a certain heat capacity or energy requirement to meet those goals or to heat the site up. That gives you the duration. So all of these things are really important to take a close look at. The other side of this, which is often overlooked, is the heat loss calculation. I mean, you're going to get heat losses to the top, to the bottom, the sides. What is your conductive and groundwater flux heat losses? What is that number, or how much percentage is that of your total input? The other thing is that all of the energy that we put in doesn't stay in. We have to extract the steam and water. So what is the percentage you assume? That actually gets you a net input. So looking and comparing different designs, you need to understand that. And once you have this net input, then this is how we come up with our number of days of what's required. So, one vendor may say it's going to take 90 days. Another one may say 160. Well, why is that? It's not because they're using a different technology, or it's not because the technology doesn't work as well as somebody else. It's because of these assumptions. So if you make generous or optimistic assumptions, you're going to end up with a shorter treatment duration. Maybe it works. Most likely it won't. You need to have a real good understanding of those numbers to understand the certainty or the probability of success of your design. And ultimately, we can use the same kind of approach to calculate all of the design factors. And again, this is going to impact your costs. So how big of an extraction treatment system do I need? How much steam am I going to generate? How much condensate do I need to treat? All of that comes from this energy balance approach. So you want to take a careful look at all of these things. Here's a site, and one thing I wanted to point out is this was a TCE site. and we use thermal conduction heating for it. And this is your mass removal rates, and this is your cumulative mass. And this is pretty typical for the kind of IS sites we treat with ISDR. They usually have NAPL, DNAPL. A lot of times it's CVOCs. And we will see this kind of characteristics where we go along, we're heating, and all of a sudden, bam, we see these peak concentrations. We see a big increase in our cumulative mass, and then it tails off. Well, what's happening here? Well, the cold boiling point of TCE in water is 76 C. So when we have pure DNAPL in the TCE DNAPL in the subsurface with water, it's going to boil at 76 C. So that's basically what you see here is the temperature heat up of this site. When we reach 76 C at this point is when we started to see that DNAPL boil, and that's where we saw that mass removal rate. Well, for this site, what that meant was we had a total of 5,450 kilograms, and we look at the peak rate of 153 kilograms per day. That's 3% of the total. That turns out to be a very good, consistent number. So if you know your starting mass, how much mass is in the subsurface, and you take 3% of that, that's going to give you your total mass loading rate. And again, how much steam you produce, how much air you need to extract to get hydraulic control, that gives you your vapor flow rate. Your mass loading rate comes from your mass estimate. So having good or making a good estimate of your mass estimate gives you that total peak loading rate. That's going to impact your selection of your treatment system as well as the sizing of that. So let's take a look at transparency and operational data. So we've gone through the technology selection, gone through design, now we're into operation. Well, these sites go pretty quick, 6 months. You don't have a lot of time to scratch your head or wonder what's going on. So what you can do is we use consolidate all the information you're going to collect from the site into a data website or a data portal. And you can look at what you want to have as a data portal like this and have access to it to be able to track on a daily basis in real time in some cases. For example, the temperatures, the heat up, whether it's in the subsurface or whether it's the operational characteristics of your treatment system, you want to be able to track those things and see what's going on, follow along with what the consultant or the vendor is seeing and recommending, and kind of anticipate if there might be problems. So what you want to look at is a range of things. We can look at temperatures in the subsurface, power and energy uses, mass removal, water balance, vapor balance, and this all ties into the energy balance, how much energy we're pulling in, how much energy we're pulling out, and how does that track with what we thought would happen at the site. So here's some examples of that. So the black line represents what was simulated. So this is the model heat up of the subsurface, and for this particular site, this is the average treatment zone temperature. So we actually did better than the model. This is what you want to see. Some sites may lag and you want to understand why. It might be an indication that geology was different than anticipated, or maybe the heating system's not running as planned. They're not able to get as much energy in the ground. Or for example, if it's an ERH site and you thought the resistivity was going to be X and it's a lot higher than that, then that's going to impact how much energy you can get into the subsurface. There's things that can be done to affect that within a degree, but you want to be able to track and see that early on and make decisions early on, not wait until the end of the project to see how it turns out. We can also look at individual sensors, or in this case, what individual treatment depths, so we can see how those are tracking. Again, you want to see them all coming up to temperature roughly at the same time period. And for this site, the target treatment temperature is 100 degrees C, so we want to see them all get to that point. That means the entire system is boiling, generating steam, removing those contaminant vapors. We're getting uniform treatment across the entire treatment volume. Power usage. This is key, again, in terms of tracking how your system's doing. Is it meeting the design spec? The black line again represents what was modeled or designed. The blue line is what we actually were able to achieve. Again, a little bit better than the model, which is awesome. And this just gives you an idea of how much energy is going into the process system versus how much energy is going into subsurface to heat and what your total energy usage is. So again, this can give you a lot of insight as to how the system is performing. Same thing with these usage rates. The black line is what was designed. We always like to do a little bit better than the design so that we get ahead of the game, and we were able to do that at this site and actually match up pretty well. And the energy balance. Again, this is key. This provides some direct insight as to how the site is heating up. Again, what I mentioned before, you start to see this green line represents the energy out of steam. So how do we calculate that? Well, we start to see condensate in our steam condenser. What that means is that the site's getting up to temperature and boiling and generating that steam. So we know how much, this should line up with your temperatures. If we're not seeing this, then the site is not heating properly. There's, again, things we need to do to fix that. And again, this net energy input, this should all match up with what we expected to see. And then at the end of the day, what we're really looking at is getting the mass out, is cleaning these sites up. So again, we have our total mass removed cumulative curve. And I should point out that all of these plots are from the end of a project. We look at these on a daily, weekly basis. You'll be, you won't be all the way out here. So we're tracking, you can track progress as you go and see how you're doing. This site, you can see where we're getting good mass removal. What's interesting here is that this peak started off, this was a TCE site, started off when the site was roughly between 75 and 80 degrees C. So again, this is where you're starting to see that DNAPL come out. The other thing we're tracking here is that when we start to see these low asymptotic mass removal rates, that's indicating, well, we combined with the temperature. So we use a multiple line of evidence. We get the site up to 100 degrees C. We look at how much steam we remove. We're seeing that steam come out. All that lines up. The site's boiling. And then we see the peak concentrations come out. That means the mass came out. So the train arrived at the station. The mass got mobilized and we pulled it out. And then we see this decline in concentration. So this multiple line of evidence approach tells us the site is cleaned up. And then the question is, how clean? Do we continue to operate this for a period of time? We never get to zero because we're treating source zones. So there's always mass on the outside, and the regulatory goals aren't zero. They're usually some number. And so this is where, when we get down into this period, where we would suggest going in and doing interim sampling, collect some soil or groundwater or both, see how we're doing, and determine whether we're ready to shut the site off and do verification sampling. And with that, I think we're done. Hopefully we've lifted the veil on both injection technologies as well as thermal remediation. And I hope we've explained or revealed something that was maybe previously not so clear or maybe a secret. And with that, I think we are done and we're ready for questions.
Awesome. Good job, guys. This is Nate Beershanks, who's having some technical difficulties, so I'm going to step in and finish this out. So let's jump into some of the questions that were submitted. The first one says, how do you evaluate the cost benefit in using Hrse for reducing uncertainties in the remediation plans?
Yeah, this is Elliot. I'll take that. Well, it really comes down to working on hundreds of sites over the last 20 years where we've done high resolution characterization and being able to demonstrate the lower life cycle costs of a project with and without it. So I would say, 95% plus of the sites we worked on where we get a better handle of mass distribution and hydrogeology and seepage velocity and flux and all that kind of stuff, that at the end of the day, these sites come in cleaned up faster and at lower cost.
Okay, thanks. Next question. What is the best way to move a potential subcontractor from sales pitch mode to actually addressing your particular concerns as a primary consultant?
Well, I would lead off with contact Elliot or me. We obviously aren't sales guys, but I think I would just say, I can't speak for everyone, but for Cascade, we have dedicated salespeople that are highly technical. Some of them have technical backgrounds in the various technologies we're dealing with. and they really are facilitating. So they're optimizing, they're leveraging Elliot and me and the rest of our technical teams to provide resources, and that's really what you want, is to work with folks who have sales teams that will help you get in contact with the people and arrange that, but then you're in direct contact with the technical people that you need to be. So whether it's on the injection side or the thermal side, very quickly, if you are reaching out to Cascade, you're going to be in touch with the technical people working on the project or working on your evaluation.
Sure. Okay. Next question. What RFP and what contract provisions do you suggest to advance the goals you will outline in this presentation? Or I guess you did outline.
Do you want to kick that off, Elliot, and then I can jump in?
I think that was the essence of our presentation today, was everything we've talked about somehow needs to work its way into a document that gives you high visibility and transparency on what's actually going to happen at your site. And so, that's really what we tried to accomplish today, is to raise the issues that need to be transparent and they need to be evaluated as you select technology.
Yeah, and I would just add on the thermal side a very clear statement of work so from the thermal, we have to select the technology. We have to come up with a design. So understand the geology, hydrogeology dimensions. The treatment goals need to be clearly spelled out, how they're going to be assessed. How many samples are you going to collect? And then a key part, hopefully, in both the injection as well as the thermal side, is the starting COC mass. And where do you think that is, as Elliot pointed out? Those are key factors. In terms of the actual contracting terms, for us, it's a little bit different maybe than the injection technologies, but things happen pretty quickly on a thermal project, and they're fairly large. So the capital outlay is kind of significant. There's the drilling, there's the materials, there's the equipment. So doing things set up in a milestone kind of progress payments based on milestone achievements, that works for us really well. And then the final thing I would just say is the bonding requirements. A lot of times we see, we're fine with performance bonding. We have good bonding capability overall, and sorry, not performance bond. Payment bonds are pretty much part and parcel to remediation work. But where it gets tricky is the performance bonding, and that adds substantial cost to a project without really, I think, adding a whole lot of value. And we'd be glad to talk, specifically about that if you have questions. But there's alternatives to performance bonding that I think are more cost-effective for the overall implementation and cost of a project that I think are just more effective without the undue cost.
Yep, that makes sense. All right, next question. How are you determining permeability on sample tested in lab or other?
Well, in the field, obviously, high-res site characterization is a great way to understand variability of permeability in the subsurface and distribution, and being able to tie that to specific geologic units that you can target with high-res, for example, using different tooling to look at EC logs or identify those zones, understand where those permeable zones are, and then tying that to specific field tests so that you have actual measurements of those zones and actual values, because it's usually just a relative indication and your direct push high res data. So you need to be able to correlate that to a real number. That's great. And Elliot, I don't know if you want to add something to that relative to field testing or lab testing that you're looking for.
I think that covers it. We do like to verify relative K values that we get with tools like a Waterloo APS or MIHPT by actually doing injection tests with water and do that, in a automated way, so we can actually get accurate flow rates and pressures and identify potential fracturing scenarios. So it's really a combination of both. But we do want to do that permeability testing where we want to target mass. So it's critical to get the mass distribution first, and then we'll get an idea of relative hydraulic conductivity, but then, the second line of evidence of a water injection test really locks it in for us.
Great. Okay, a few more. What are applications of this ISS technology to stabilization of PFAS source area soils, particularly in light of recent reductions in PFOA and PFAS health advisory levels?
Yeah, I think you meant ISTR. ISS, in situ soil stabilization, is a different technology, but ISTR. So first off, ISTR for treatment of PFAS, or thermal remediation for treatment of PFAS, we're targeting temperatures of 350 to 400 C. So although there are sites that we could do that in, it primarily would be vadosome sites. Anytime we're below the water table, it becomes almost technically impractical to guarantee or sheet pile and guarantee that you're not going to have some groundwater flux in. And if you have just a little groundwater flux in, it's going to be very difficult to uniformly get to those temperatures, well above 100 degrees C. So what we are seeing and looking at increasingly is excavation of those PFAS source zones. So PFAS contamination, you want to, just like with CVOCs, you want to identify your source zone, then you have a plume, and it might be multiple remediation scenarios where you excavate and treat your source zone, you have a barrier to reduce flux, and then maybe you have some plume treatment. It can be a combination of approaches that need to be considered to address the risks at a site. But relative to thermal treatment of PFAS, we would extract that or excavate that soil, get it in an above ground pile. Now we don't have to deal with groundwater. We can design an effective pile. We have done effective pile treatments for dioxin PCBs, similar temperatures, 400 degrees C, treatment of 60 to 70,000 cubic yards at a time, so large piles. It's a very effective treatment technology for that. In terms of meeting the health advisories that are out there, that's what we've been able to achieve, relative to other contaminants of concern, as well as the work we've done on laboratory at a laboratory scale basis for treatment of PFAS. So yeah, I mean, it's anytime the goals are lowered and lowered and lowered, it's more of a challenge, but I think it's very doable with thermal treatment. Just a point I would make here is that I think there's PFAS is interesting in that it's not clear direction on what's required for treatment, what's required for off-gas treatment, what's allowed for discharge, and specifically, we don't have necessarily the analytical methods to track all of this. Some of the analytical methods that we're using are only looking at maybe 30 specific compounds, and there's thousands of these compounds. So I still think it's early in the game relative to what's going to be or how it's going to be done and what's the right approach. But everything that we've seen, not just the work we've done, but that others have done relative to thermal treatment of soil for PFAS removal, shows real promise there. So yeah, and again, reach out, give us a call or contact us. We'd be glad to share some of what we've seen and what we've just completed recently in some interesting lab work.
Excellent. Okay, last question, and I can take this one. It just says, will you be providing a copy of the slides from this presentation? So we can do that upon request. Reach out to us. You can shoot us an email at communications@cascade-env.com, and we'd be happy to shoot you a PDF of those slides. And with that, I can start wrapping things up. So thank you, John and Elliot, and to everyone in the audience today for taking time out of your busy schedules to attend today's webinar. We really hope you enjoyed today's session. A recording of the presentation will be circulated to all those in attendance within about a week. Our next webinar is going to be on August 10th. It's titled, How Understanding a Site's Conceptual Site Model Can Prolong the Life Expectancy of a ZVI PRB Remedy. You can register for it at cascade-env.com/resources/webinars. The next Think Thermal webinar is going to be on August 16th, and it's the first part of a two-part series covering in situ thermal remediation challenges. You can register for that one at terratherm.com/webinars. And finally, as you log off today, you're going to receive a very brief survey. We thank you in advance for providing feedback on today's session. We really do read every survey in an attempt to improve our presentations moving forward. And with that, thank you guys and have a great day.
Thank you.
Yeah, thank you.